Okay, so I have three different scenarios here of cells being immersed in a solution. These are the water molecules, the blue ones, and then the yellow ones are the solutes. The magenta color is obviously the cell. So let's assume, we're going to assume that the cellular membrane, this phospholipid bilayer, is semi-permeable. So it only allows water molecules to pass in and out. So a water molecule could go from the inside to the outside, from the outside to the inside. But we're going to assume that it doesn't allow the passage of the solid particles. So that's why it's semi-permeable. It's only permeable to certain things. Or we could say selectively permeable. So what do we think is going to happen? So we can see here, obviously, we have a lower concentration of solute on the outside than we have on the inside. So at any given moment of time, you will have some water molecules moving in just the right direction to go from the outside to the inside and from the inside to the outside. But what's more likely to happen, and what's going to happen more over a certain period of time, is that the water molecules that are on the outside, and we talk about this when we talk about osmosis, so they're going to be less obstructed by solute particles. So if this happens to be moving in that direction, it's going to make its way to the membrane and then maybe get through the membrane. So the water molecules on the inside are more obstructed, so they're less likely to be able to fully interact with the membrane or move in the right direction. And they're being obstructed by these solute particles. Okay, and so even though we're going to have water molecules going back and forth in a given period of time, you have a higher probability of more going in than going out. So we're going to have a net inflow here. And I read that in a second. So we have the net inflow of H2O, of the water molecules. So in a situation like this, when we're talking about a cell and it's in a solution that has a lower concentration of solute, it's important to know that we're talking about a solid. So it's not allowed to go to the membrane. The membrane is not permeable to that solids. So we call this type of situation, this type of solution, is a hypotonic solution. And so anytime we're talking about hypotonic, we're talking about relative concentrations of solute that cannot get through some type of membrane. The word hypo, it's a prefix that means less of something. So in this case, we have a lower concentration of solute in the solution than we have inside of the cell. And because of that, you're going to have osmosis. You're going to have water molecules going from the outside to the inside. So that's actually going to put pressure on the cell. And the cell itself might expand, or it could even, if there's enough pressure, it can explode. So it will swell up, and it can burst, explode, whatever you want to call it. Okay, now for this next scenario, we have the same, so there's no net outflow or inflow because the water molecules are going in and out. It's like the same. So in this situation, the probability of a water molecule in a given period of time going from the outside to the inside or from the inside to the outside, it's going to be the same. So you're not going to have any net inflow or outflow. It's always going to have the water molecules going back and forth, but there's not going to be any change. So the cell stays the same. That's what iso means, the same. So it's staying the same. So when you have the same concentration of solute in the solution as you do inside the cell, that's why we call it isotonic. It's an isotonic solution. It has the same concentration of solute and you have no net inflow. So then obviously this last one is a hypertonic solution. So hyper means more. So this is a hypertonic solution. Once again, the solute can't go across the membrane, but the water molecules can. You're going to have water molecules going from the outside to the inside and from the inside to the outside. the probability that the ones on the inside are going to be less obstructed to go out than the ones on the outside to go in. So you're going to have a net outflow. So higher probability of things going from inside to the outside than outside to the inside, because they're going to be more obstructed. So they're going to be held back. In this situation, you're going to have the water escape the cell, and the cell actually might shrivel up since it's going to lose that pressure from the water. It's like being dehydrated. The cell itself might shrivel up in some way. And you can actually see this in actual living systems. If you were to put a red blood cell into a hypotonic solution, the water is going to rush into it and it's going to blow up. So it's going to basically expand like a overinflated red blood cell, like a balloon. And it just expands and it can burst. And then in an isotonic solution, it's going to look the way that we're used to seeing a red blood cell, because it's having the same, it's staying the same. And then in this hypertonic solution, it will shrivel up and shrink, looks kind of like dried up cell.